There are 2 trillion galaxies in the observable universe. Each one contains hundreds of billions of stars. Most of those stars have planets. Many of those planets sit at the right distance from their star to allow liquid water on their surface. The numbers are so large they stop feeling real. And yet in all of it, across all of that space and all of that time, we have found evidence of life in exactly one place, here. The question of whether that is because life is everywhere and we have not looked hard enough, or because life is genuinely rare and we are genuinely alone, is the most important unanswered question in science. This is where the search stands right now. This is Beyond the Cosmos. We go deep on space science, one question at a time. Subscribe and stay with us. This one might change how you see the sky tonight. Before we can ask whether life exists elsewhere, it helps to understand how fragile or robust the process that created it actually is. Life on Earth began somewhere between 3.5 and 4.1 billion years ago. The planet itself is only 4.5 billion years old. Life did not take long to appear. By cosmic standards, it was almost immediate. That early life did not emerge in a warm, comfortable pond. It appeared during a period called the Late Heavy Bombardment, when Earth was being struck by asteroids at a rate far higher than today. The surface was volcanic and unstable. The atmosphere was nothing like the one we breathe now. And yet something happened. In the deep ocean, near hydrothermal vents that pumped chemical energy into the surrounding water, the first self-replicating molecules assembled. Not by design, by chemistry. The right molecules in the right concentrations under the right conditions began copying themselves. That process, once started, never stopped. It has been running continuously for nearly 4 billion years, producing every living thing that has ever existed on this planet. What this tells us is important. Life did not require billions of years of preparation. It did not require stable, gentle conditions. It appeared almost as soon as the chemistry was possible. That suggests the process may not be as rare or as fragile as it might seem. But appearing once, on one planet, in one solar system, is not a sample size that tells us much. It is still a sample size of one. One of the most important things biology has taught us in the last 50 years is that life does not need comfortable conditions. We have found living organisms inside the cooling chambers of nuclear reactors, in the hyperacidic drainage of abandoned mines, where the water is more acidic than battery acid, at the bottom of the ocean under pressures that would crush any human being instantly, inside solid rock kilometers below the surface, feeding on hydrogen produced by chemical reactions in the stone. These organisms are called extremophiles. They do not merely tolerate conditions that would kill everything else. They require them. Remove the heat, the acid, the pressure, the radiation, and they die. What extremophiles demonstrate is that the range of conditions under which life can exist is far wider than anyone assumed before we started looking. The narrow band of temperature, pressure, and chemistry that we think of as habitable is the range that humans require. Life itself requires much less. This matters enormously for the search beyond Earth, because once you remove the assumption that life needs Earth-like conditions, the number of potentially habitable environments in the solar system alone expands dramatically. And across the galaxy, it expands into numbers that are genuinely difficult to comprehend. The most compelling candidates for life in our solar system are not planets. They are moons. Europa, a moon of Jupiter, has a global liquid water ocean beneath a shell of ice estimated to be between 15 and 25 kilometers thick. That ocean has been in contact with a rocky seafloor for billions of years. Hydrothermal vents, similar to the ones where life may have first appeared on Earth, are considered likely. The ocean contains more liquid water than all of Earth's oceans combined. Enceladus, a moon of Saturn, is even more direct about what it contains. It actively vents water vapor and ice particles from its south pole into space, forming one of Saturn's rings. Analysis of those plumes by the Cassini spacecraft confirmed the presence of water, sodium, carbon dioxide, molecular hydrogen, and complex organic molecules. Everything on that list is consistent with hydrothermal chemistry that could support microbial life. Titan, Saturn's largest moon, has a thick nitrogen atmosphere and lakes of liquid methane on its surface. It is not a water-based environment, but it is a complex chemistry environment, and some researchers have proposed hypothetical biochemistries that could function in liquid methane the way Earth biochemistry functions in liquid water. Mars is the most studied candidate. Evidence of ancient riverbeds, lakebeds, and mineral deposits that form only in the presence of liquid water tells us Mars once had surface water. Whether anything lived in that water, and whether any microbial life persists in protected subsurface environments today, remains unanswered. Multiple rovers and landers have searched. Nothing definitive has been found. Nothing has been conclusively ruled out. We have not left our own solar system. We have barely scratched the surface of the objects within it. And already the list of plausible candidates is longer than most people realize. Until 1992, we had no confirmed evidence that planets existed around any star other than the Sun. The existence of other solar systems was assumed but unproven. Today we have confirmed over 5,000 exoplanets, with tens of thousands more candidates awaiting verification. The methods used to find them, primarily detecting the dimming of a star as a planet passes in front of it, are biased toward large planets close to their stars. The actual number of planets in the Milky Way is estimated in the hundreds of billions. Among those confirmed planets, several hundred sit within the habitable zone of their star, the range of orbital distances where liquid water could exist on a rocky surface. Some of them are close to Earth in size. Some orbit stars that are stable, long-lived, and similar to the Sun. The James Webb Space Telescope has begun analyzing the atmospheres of exoplanets by measuring how starlight filters through them during transit. What scientists are looking for are biosignatures, chemical compounds in the atmosphere that could only be present in significant quantities if biology were producing them. Oxygen combined with methane is one example. Both gases react with each other and would quickly disappear without a continuous source. On Earth, that source is life. No confirmed biosignature has been detected in an exoplanet atmosphere yet. The technology is new, and the measurements are difficult. But the capability now exists in a way it did not a decade ago. We are, for the first time in human history, capable of detecting the chemical fingerprint of life on a planet orbiting another star. We have not found it yet, but we are looking. If the universe is as large and as old as it appears to be, and if the conditions for life are as common as the numbers suggest they should be, then where is everyone? The Milky Way is approximately 13.6 billion years old. Earth is only 4.5 billion years old. Any civilization that arose in our galaxy, even 1 billion years before us, would have had a billion-year head start. That is a long time by human standards. By galactic standards, it is brief. Perhaps life is common, but intelligent technological life is extraordinarily rare. Perhaps the step from simple microbial life to complex multicellular organisms is a nearly impossible transition. Or perhaps, and this is the resolution that most scientists are reluctant to voice, we genuinely are the first. The first to develop this kind of technology in a galaxy old enough to have produced 1,000 civilizations before us. If this question matters to you the way it matters to us, subscribe to Beyond the Cosmos. Like the video if it made you look at the sky differently. Turn on notifications so you never miss what comes next. And leave a comment below. Do you think we are alone? I want to know where you stand. I read every single one. The science may finally have an answer.